In problem 33, we're going to go over some properties of the complex exponential function that are helpful. So the first part A is that if we look at the modulus of e to the z, it's the same. Well, it has the same modulus as e to the x, namely it's just equal to e to the x. Namely, the imaginary part does not contribute to the modulus. So let me recall here that e to the I theta is cosine theta plus I sine theta. In particular, the modulus of e to the I theta is 1 because it's on the unit circle. So for this first part, when we're looking at the modulus of e to the z, if we write z as x plus iy, that's e to the x plus iy, modulus of that. And by rules for the complex exponential, it obeys the usual rules, namely it breaks up under multiplication, addition in the exponent and turns that into multiplication. And then the modulus itself breaks up under multiplication. And e to the I times a real number has modulus 1, because that's going to be a point on the unit circle. And then e to the x is the exponential function. The exponential function is always positive. So the absolute value, or modulus, if we want to consider it as a complex number, is already always positive. So we get e to the x out of it. And so the modulus of e to the z is e to the x times 1, which is e to the x. Great. So that's something important to remember. So let's highlight that. Now, the part B is asking, does e to the z equal 0 have solutions? We know that's false for real numbers. So if z was x, that would be false. Namely, e to the x is always positive. And so the question is there a difference now that we're in the complex realm? And we're going to find the answer is no. So suppose it did. Then this would tell you that the modulus of e to the z would be the same as the modulus of 0, which is 0. But the modulus of e to the z is e to the x. So this tells us that e to the x is 0. And this is a contradiction. Blue lightning has struck. That's impossible. So the answer is, of course, no, it doesn't. So it's just like the regular exponential function. Now, the part C of this question is to show that this is actually a periodic function with period 2 pi I. And periodic, it's sort of complex periodic. The regular exponential function is not periodic, but this guy is. And roughly the periodicity comes into play because a portion of this function involves cosine and sine, and those guys are periodic. So let's unravel what this statement is saying. This is saying that e to the z is the same as e to the z plus 2 pi I. That's what it's saying. So let's show that. So let's start with e to the z plus 2 pi I. We know that we can break apart our function as such. And e to the 2 pi I is cosine 2 pi plus I sine 2 pi. Sine 2 pi is 0, cosine 2 pi is 1. So we get 1 plus I times 0, which is 1. So that's e to the z times 1, which is e to the z. So on the far left side of our computation, we have e to the z plus 2 pi I. And on the bottom, we have e to the z. So periodic with period 2 pi I.